Let's dive in conditional probability. Again, simple concept, but the notation can trip you up sometimes. So let's just dive into what that notation is and what it means. Now the basic concept of conditional probability is that if I have two events that depend on each other, I can make a statement about the probability of that second event occurring given that the first occurred. Now the notation that we are going to use, there is a P A comma B, and that means the probability of both A and B occurring independently of each other. And then we have P of B by A, that's the probability of B given that A has occurred. So that implies some dependency between B and A, and we can tie this all together using this handy dandy equation here, where the probability of B given that A, that is the conditional probability of B given event A, is equal to the probability of A and B together divided by the probability of A. So you can use that to tease out the conditional, the dependence between B and A. It will make more sense with a real example. So let's take a look at a real example. Let's say that I give my students to test and overall 60% of my students passed both tests. So if we call the test A and B, probability of A comma B would be 60%. However, the first test was easier, 80% of my, so if B is the second test and A is the first test, P of A would be 80% in this example. You can see this gets confusing pretty quickly with all the A's and B's and commas and types, but let's review again. So 60% of the student passed both tests, so P A comma B is 60. The first test was easier, 80%, so P of A is 80%. Now how do I figure out the percentage of students who passed the first test, who also passed the second? So what the probability of passing my second test given that you pass the first test? That's conditional probability. So we are asking for the probability of B by A, that conditional probability of passing test 2 given that you pass test 1, and we can compute that using the equation that we just saw, P B comma A. The conditional probability of B given A is equal to the non-conditional probability of P A comma B, which was 60% over the probability of A, which is 80%, and if we do that division we end up with 75%, and we can say that 75% is the conditional probability of passing the second test. Given that you pass the first one makes sense. Hit pause and digest this for a minute, because with all these letters and different punctuation marks and what not, it can get confusing. So let me just dive you into a notebook and you will go through a bunch of other examples to try to make this notation and how to handle all these things second nature to you, and when a little bit of an exercise so you can practice that yourself. Okay, for this exercise I want you to open up the conditional probability exercise notebook in your course materials, and I will try to walk through this and a little bit slowly. This is a sort of a tough thing to wrap your head around a little bit. What we are going to do in this activity is generate 100,000 random people, and let's say that they are all customers on a big e-commerce website like Amazon or something. For each of these 100,000 people, we will randomly assign them to a given age range, being in their 20s or their 30s or their 40s all the way up to their 70s, and we are going to create a conditional probability of a independency between their likelihood of purchasing something, dependency of likelihood, and their age. Basically we are going to say that the older you are, the more likely you are to buy something. So if you are young, you will have a lower probability of purchasing something. So let's say that we say the probability of purchasing something is called E and the probability of actually being in a given age range is F. That means that we on have a dependency, a conditional probability between E and F. Alright, so let's walk through the code here that sets up that random data set. I get a lot of questions from people about how this code works, so bear with me guys if you do know Python already, but for the people that are new to it, this does take some explaining, so I am gonna going by line. Alright, so we are gonna start off by importing random from the NumPy package. Nothing exciting there, that's just so we can actually generate random numbers within this little snippet of code here. Random.seed just generates a seed value for the random number generator. The purpose of this line is to make sure that we get consistent result every time we run this code. So as before we used to get different result every time you run this, but by having a consistent speed number, that means you will get the same result back for our random numbers each time that we run this. The number 0 is arbitrary, all that matters is that it's the same value being used each time. It could be 1, 2, 3, 4 or any number you want as long as it's the same one. That's all that's going on there. We are just making sure we have some consistency in our result. Next up, setting up two Python dictionaries called totals and purchased. Total and purchase are two dictionaries. What this is going to keeping track of how many total people I have in each age range. The 20 years older, the 30-year older, the 40-year olders and so forth, and how many purchases were made by each person in those age ranges. So basically I am saying initially I have two 0 people in this 20-year-old bucket. 0 I purchase from, and 20-year-old 0 purchase from, 30-year-old 0 purchase from, 40-year-old and so on and so forth. So this is just how I am gonna keep track of the total numbers associated with each age group. I will also keep track of the total number of purchases regardless of age with the total purchases variables. Next we are going to create a loop to iterate through 100,000 random people that we are going to create, and that underscores just a placeholder. I could just say for x is range 100,000 or whatever you want, but since I am not actually using that value anywhere within the loop, here I can just use the underscores character as a placeholder. It just means I don't really care what that value actually is each time, so I don't care that this is user number 1776 1776. I can just discard that number. That's all the underscores means. It means I don't really care what the actual number is. So for each of these 100,000 peoples we are gonna iterate through this loop many times, and for each time we will assign age decade to this person. Random choice will just randomly pick a value out of this list, so we pass in. So we will randomly pick one of these numbers, 20, 30, 40, 50, 60 and 70 evenly distributed. So we will make a random even chance of being a 20-year-old, 30-year-old or 40-year-old and all the way to 70-year-old for each individual person. Now here where things get a little bit weird based on your age, we compute a purchase probability. So we are taking your age and dividing it by 100 to figure out the odds of you actually purchasing something from our website. So for example, if I am in my 20s, I will take 20 divided by 100. That works out to 0.2 or 20%. A 20-year-old will have a 20% chance of actually buying something. 30-year-old will have 30% chance of buying something, and so on and so forth. This is how we are figuring out that younger people are less likely to buying something than older people. In our randomly generated data set here, as we go through it will bump up the total for that age decade by 1, mean that we have generated to a new random person with this age range. And there we are saying if random dot random is less than that purchases probability to actually attributes a purchase to this person. How does that work? Well, random dot random just randomly selects a value between 0 and 1. If that random number is less than or purchase probability, we say this person actually bought something. Let's look at an example to make that a little bit more intuitive. Let's say that we have a 30-year-old, okay, or someone in their 30s, their purchase probability will work out to 0.3 or 30%. So if our random number between 0 and 1 comes to be less than 0.3, that person is attributed to a purchase if it's greater than a 0.3. They did not buy. So you see how that works is how we are basically rolling the dice to see if this person bought something or not given their overall probability of purchase for their age range. So as we are done, we are building up these a total number of purchases that are done across the entire data set. We are also keep tracking of purchases for that individual age decade, and we are also keeping track of the total number of people in each age decade as well. We'll need all these numbers to figure out things like P of E and P of F and P of E given F and all that stuff. Let's go ahead and run this, and that generates our fake data set that has a dependency between age and purchases. Let's take a look at that work. I would expect the total for each range to be roughly consistent, and we have about 16,500 people in each age decade. So that's good, a nice even age distribution, that's what we expect. But if we look at the purchase attributed to each age range, you can see that is increasing based on age. So we have that dependency that we try to model in there working nicely. So about 3,020-year-old purchased something, but about how almost 12,000 also bought something, even though that they were evenly distributed in number of people. So we are seeing here very clearly that there is a relationship between your age and your likelihood of purchasing something. Okay, so we have a nice little fake data set to work with here for conditional probability. We can also compute the total number of purchases across the entire data set. That comes out to 45,012. And now we have the values we need to work with for playing with conditional probability. Okay, so again a lot of this is just getting your head around the notation and keeping track of what letter means what. So again we are gonna call E purchasing something and F the given is that you are in. So let's start by computing P of E given F. This is a conditional probability of between making a purchase, and F where we are gonna call that being in your 30s will just arbitrarily select an age range there. So the probability of purchasing something E given that you are in your 30s, F we can compute that directly actually. So we can just figure out how many 30-year-olds bought something as a percentage. So let's go ahead and just compute that how many total purchases did we see from 30 somethings and how many people were in that data set, and that works out to 0.99, almost 0.3, right? We can also independently compute piece of E and piece of F. Piece of F will be probability of being 30 overall in this data set. That's easy. So we will just take the total number of 30 years olds divided by the total number of people, and that works out to 16.6%. 1.6166 piece P of E is just the overall probability of buying something regardless of your age. If there was no dependency there at all, so to compute P of E, we will just take the total number of purchases across everybody regardless of age divided by the total number of people overall. And that works out to 0.45 or 45%. So overall in our entire data set, taking age out of the equation, there is a 45% chance of buying something. So this is where you start to put on your thinking cap a little bit. So wrap your head around this statement. If E and F, that is buying something, and your age were independent, then you would expect P of E given F to be about the same as P of E, right? If there was no dependency between buying something and your age, you would expect the overall probability of buying something to be the same as the probability of buying something given your age. Because there should not be a dependency, there should not matter, F should not matter, but we have seen that that's not right, true. So P of E we computed be about 45%, but P of E given F we computed earlier to be about 30%. 0.299, whatever it is, these numbers are fairly different. So that alone is telling us that E and F are dependent, that there is a condition between these two things. And we know that's the case. In this example, we artificially created a dependency between purchases probability and age. So that's one way to tease that out of the data right there. If you see that P of E and P of E given F, or if you want to use different letters, you can P of A is not equal to P of A given B. Whatever letters you want to use, it's just notation. If those are not the same, then there might be a dependency going on there that you need to know about. All right, let's also compute P E comma F. Again, this is all about notation. P E comma F is different from P E upon F. So P E comma F is the overall probability of being both in your 30s and buying something with a dependency there. So we are looking at the overall probability of being both in your 30s and buying something, not just restricting that to the population of people that are in their 30s. We can compute that easily enough. We can just look at the total number amount about the total size of the data set here, and that works out to about a 5%. 0.049. While we are at, we can also compute the product of PE and PF. That's just going to be multiplying PE and PF, the overall probability of buying something and the overall probability of being in your 30s. That comes out to about 7.5%. Now in statistics, when they talk about probability, you will often see the relationship that P of E comma F is equal to the product of and E and F, but that is only true if E and F are independent. Now if we found here that P of E comma F, the overall probability of just being in your 30s and buying something out of the total data set is about 0.05, but P of E times P of F is about 0.075. So when you have a dependency going on between these two variables, there is a conditional probability going on, and the relationship of P of E and F equals P of E times P of F no longer hold. So that's another way you can kind of figure out that maybe there is a dependency going on here that's messing up your results. However, we can go back and check that equation that we gave back in the slides and just see if P of E given F is in fact equal to P E comma F over P of F, and that's just a way of computing conditional probability. If you cannot compute it directly as we could in this example, and sure enough we can prove that that is true. The probability of E comma F, that's just going to be the total number of purchases from 30 years old over the entire data set over P of F, which we computed earlier. That does work out to 0.2999, which is exactly the same as P of E given F that we computed way at the top of this. Right, so let's double check that 0.299295 same number that we got here originally. So that's cool, the math works out. Wow, okay. So this is basically a couple of ways to figure out if you have a dependency in your data that you might not have known about, a way of computing conditional probability given other things that you might know. So anyway, let's do a little assignment here, a little bit of a challenge if you will want. So your task, should you choose to accept it, is to modify the code above such that the purchase probability does not vary with age. So remember up here in this first block up here, and we had this purchase probability that was a function of your age. Just make that a constant value, instead see what that does to your results. So if you do that, can you generate a new data set where you can show that P of E given F is about the same as P of E. That would show you that there is no condition there. If you show that to be true, that P of E given F is the same of P of E, then there is not a dependency those two things, and that's a mathematical way to find that. So give